Okay, so welcome back again to the class. So today we will still continue with register transfer level RTL design. So last week we have learned this, yeah, RTL notation. All right, is the syntax that we will use to create the RTL code or RTL program, just like this. And we have then our first example here, 5.1, right? And we have write the code for this, okay, and look at the simulation result already. Okay, so today we will continue what we have done last week, which is the design flow or the RTL design flow. Okay, uh, so after this, yeah, we will start the design with this. Last time we start with RTL modeling. Next, in the next chapter, we will start with algorithmic modeling. We start with algorithm, all right, and we try to create the RTL modeling, and we will design the DU circuit and the control unit, all right, and also the CU DU integration, all right, the one that we did last week. Uh, and after that, these are the flow, all right, that we are very familiar with. The logic synthesis using the Quartus 2. All right, design verification is simulation, yeah, and physical design and implementation is to download the design or to configure the actual FPGA. Right, we don't do this in our class because we don't have access to the hardware for now. Okay, now today we will look at example, the next example, 5.2, and also do some exercise here, right? And hopefully we can finish this chapter by today. This is another example where we have the data path given here. All right, we have the register, two registers, rec 1 and rec 2. We have the ALU here, and we have the three-state buffer, yeah, to enable here the data here from to enter to the bus. All right. So the question is this: suppose you are required to design a digital system that implement the function f equal to x plus y by using a data path block diagram given in figure. This is figure 5.10. All right. The circuit will only perform the operation when the start signal is asserted. All right. So we have the start signal. The LLU operation are controlled by the OP signal, where if OP equal to 0, F is equal to A, means that the output F here is equal to the input A here, means that we just pass this signal from this input to this output. While is OP equal to 1, F, the output here is equal to A plus B. So means that if OP equal to 1, the output here is equal to A plus B. Right, so we want to do this and to implement the function of x plus y, so meaning that we want to plus a number, right, any number. X is variable. Okay, so this is the code Verilog program for the data path. So we will try to write this in Quartus later on. Okay, but look at how we create the ASM chart, all right, to implement this. Okay, so here at 0, we will stay at 0 with no operation. all right, because we will wait for the start signal, right, the start signal, okay, to be asserted. And if no start, we will wait, always wait here, okay. And if start equal to 1, we will start the operation, all right, until the end here. So just like this, specification, the circuit will only perform the operation when the start signal is asserted, all right. And the operation is this, all right. So we have to register. If we look at this, yeah, we have to register, and the input to this register is from this, right. So if you want to do x plus y, means that one should be in x, or y should be in one register, x in one register, and other y in another register, so that we can add, right. And the result is stored in either register 1 or register 2, depend on what we want. In this case, it is not specified where to store the result, so we can choose either one. So in this example, the result is stored in register 1, means that we insert x in register 1, all right, and maybe we save pass x to register 2 and put y in register 1, and after that we add and we put it back in register 1. So the process is like this. So we next we can write the RTL code here, where x is inserted, yeah, in or x is transferred in rack 1, all right. So we transfer x to rack 1 first in the first state here, all right. Next, we transfer the content of register 1, rack 1, into register 2, all right. So this is the RTL code. Rack 1 is transferred to rack 2. This is the content, which is x. X is transferred to rack 2, all right. Now x is in rack 2. The next cycle or next state, we transfer y into rack 1. Now y is in rack 1 and x is in rack 2. And the last cycle or last state is to add these two, all right. And so this is y, this is x, and we save the result in rack 1, right? X plus y, y here, rack 1, x, x here, y plus x here, and we store in rack 1, and we go back to wait for the next start. For example, if x and y change the value, so we start again and do the operation. All right, so this is the FBD of the CU, and this thing is for designing the CU, because we will activate the signal, right? We call it control vector here, the signal to sequence the operation in the DU here. All right. So now let's try to write the code to describe this circuit first before we create the circuit to describe the CU based on the RTL CS table. Okay, so let's do this first. Yeah, the circuit. All right, and remember, when we want to write the code, this is different from what we code in computer programming. All right, computer programming is a sequence, is executed in sequence, and the program is executed in sequence. And this is different from hardware programming. HDL is hardware description language, means that the language that we use to describe the hardware. Okay, so the difference is that in computer programming, we use the program to instruct the microprocessor to do the job. First step, what the microprocessor need to do. Second step, what the microprocessor need to do, and so on and so forth. All right, but hardware description language, HDL, is used to describe this hardware, how the hardware is designed. All right, how the uh, this, for example, how the this register is designed, and how is it connected to this ALU. All right, how this multiplexer is connected to this. Right, so we describe the structure of the circuit, the hardware. All right, and when we describe this and this and this, right, and it's in parallel, concurrent, not in sequence like in computer programming. All right, so that's why some of you may when you code, when you do the coding, the Verilog coding. All right, when you synthesize your design, you may get too many warning. All right, so that is because uh, your code is sometimes cannot be synthesized to the correct circuit. All right, so in order to write the code for Verilog or other HDL languages, for example VHDL, all right, you need to make sure that your code is synthesized or will be synthesized to the correct hardware, to the correct circuit. For example, if you want to create the multiplexer, you need to know exactly the code that you write it will be synthesized to a multiplexer. All right, so for example, if you have if statement, all right, you need to make sure that your statement or case statement, you need to make sure that you have all the possibilities. All right, if you have two input, you need to have four possibilities. Right, if you have three input, you need to have eight possibilities. If you don't have eight possibilities, the Verilog compiler will assign automatically to you, and it will create the memory, for example, so you will get the warning. All right, because the Verilog will check everything. So uh, it cannot be synthesized into the combination circuit, for example, or sequential circuit. So it will give you warning, or maybe some connection problem. All right, so that you need to practice in order to do that. All right, so now we will practice again how to create this circuit that can be synthesized by this by the Verilog. All right, so let's open the Quartus 2. Okay, we have Quartus 2 open here. Okay, so we just need to have this. And try to create a new project. This is example number this is CU for example number 5.2. Okay, here we can finish. Okay, so now we have the module. The name should be this, And if we look at this, we have many inputs and output here. So let's go to the very common one, which is the clock and the reset. All right, and we have the SEL1, OP, LD1, LD2. So this is LD1, LD2. And what else you have? You have SEL, SEL. You have OP. You have enable EN here, right? And you have data in for input. You have one output here, data out. And again, this is for simulation purpose. We want to see what is inside rack 1 and rack 2. And we create the output here so that we can see in the output. Yeah. So in this case, we add here connection to the output. The name is rack 1. And here also connection to the output. The name is rack 2. So that we can see the content of the register in the simulation. So just put it rack 1 here, rack 2, right? Okay, so we have input, the 1-bit input, this, okay, 1 bit, EN, OP also 1 bit, right? OP and EN also 1 bit. This one is 1 bit because we have 0 and 1 only. EN also 1 bit. So this is 1 bit. Okay, anything else for 1 bit? No. SEL also, right? SEL also 1 bit. Okay, data in is 4 bit. 4 bit, okay. And we have output. Four bit. Data out. And we also have these two additional, rack 1 and rack 2. Okay, and this one must be declared as write data type also, because this one we will describe using the behavioral modeling in the always block, and this one also. So we need to have write here, right? So now we want to describe this mux, right? Multiplexer. So you can describe using behavioral modeling or data flow modeling. So if you choose to use data flow modeling, you need to have or even behavioral modeling, you need to have this label. All right, this wire is labeled as R1 in, right, or any other name. If you use the data flow modeling, so this must be declared as wire. If you use the behavioral modeling, you need to declare this as write. Yeah, and the size is 320 R1 in, Okay, and we want to describe this. So how to describe? So if we use the we call it mux, we use the data flow modeling sign R1 in is going to depend on this select input, and if select equal to 1, so the output art in should be equal to data in, and if select equal to 0, it should be data out. Should be equal to data out. So this code, this line of code will exactly synthesize into this multiplexer. All right, this is called synthesizable code. All right, means that we know exactly this one will be synthesized to this multiplexer, right? And then we want to describe this register and also this register. So maybe we describe separately. Red one, we call it this one, and we use a behavioral modeling, right? And it is post age clock and post age reset. Okay, and if reset, so the output of this register will be equal to 0. What is the output of this register? The name is this, the right one. Right one is 0, right, or 4-bit 0. Else, if not reset, the output of this or the content of this register will depend on this signal LD1. So we will look at LD1, right? If LD1 equal to 1, means that 1 should be equal to out1. This the input out1 in. Right? Do we need to else this one else if, right? Do we want to write else here? No need, yeah, because the Verilog compiler will know that if we write like this, we will create the flip-flops where the if LD1 equal to 0, so the output of 1 will remain the same, remain unchanged. All right. So this will exactly create this. All right, will be synthesized to this. All right, and we want to create this one. So to create this one, actually it is a same type of register, so you can reuse this code. Just change this. So this be rect2 now, and this is LD2, of course. This is rect2, and the output when LD2 equal to 1 is this, right? Data out. Okay, so that is this. And now we want to create this ALU. All right, this ALU. So so this ALU only has two operations, right? When OP equal to 0, do this. When OP equal to this 1, do this, right? And this is combinational circuit, all right? But we can describe using behavioral modeling also. And the easiest way is to describe using behavioral modeling, right? So if this is a combinational circuit, so we need to list, if we use always block, we need to list the sensitivity signal, all right, in the sensitivity list. So it should be the input OP, A, not A. A is here, right one, and right two, okay. And we can include this en, all right, because let's get the output here. So en is included in this, all right. So now we can use a case statement, all right, to create this, so case. So the output here will depend on two signal actually, right? OPN, EN, right? So we can have we can combine these two signal, right? So we can use concatenation, OP and EN, all right. So the first thing is that we have 2 bit. So if this is 0 and en equal to 1, all right, 0, OP equal to 0 and en equal to 1, so 0, 1. So data out should be equal to what? To this, right? Red 1, and if en equal to 1 and OP equal to 1, all right, data out will be equal to red 1 plus red 2, all right. And other than that, all right, we can use default data out is no connection. Yeah, you can use this and case, all right. So this will give you this, okay. Or you can write a different type of code where you can do something like this, yeah. We can have begin, and we can use if else, if, right, if en something like this, if en equal to 1, if en equal to 1, all right, and op equal to 0, so we can have, and op equal to 0, data out equal to red 1, else if en equal to 1 and this n you need to use the logical n, and OP equal to 1. So what you do is data out equal to rec1 plus rec2, right? Else, if not that, not other than that, else, maybe we say that else. So the output data out is equal to this. It should be 4-bit, right? Not 2. Okay. Same thing here. This is same code with the previous one, but we use else if, yeah. Okay. And for the previous one, this one, this is 4-bit also, right? So you can use either one. And now we end the module, right? This is done for this, and we save and try to synthesize this to check whether anything wrong with that. We have 6 warning, and this warning is actually because of this this. So remember, if you have many warnings, you need to check, have a look at that, what is the warning is all about. And this one is the creation of trace state buffer, right? For this, for this, because of this, so should be no problem, because if you change this to 0, it should be no problem, all right? Should be no problem. But when we don't want to have 0, we exactly want the Verilog compiler to create a 3-state buffer for us. So we have this. Okay, so this is our design, and now we want to design the CU. All right, and of course the CU is like this, yeah. Okay, and to create the CU, we need to have this RTL CS table. All right, so how to create the RTL CS table? So we need to look at this. All right, so for example, in this S0, no operation. So here the activated signal is none. No signal should be activated. All right, or we can leave it is at 0. Right, nothing. We do nothing here. And next, in S1, we want to transfer X in to rec1. So means that we want to do this actually. Yeah, our X is in here. We want to put in rec1. So what we do is we need to set this cell to 1 so that X can be available here in R1 in, and to load R1 in into rec1, we need to set LD1 equal to 1. So that's why we have this LD1 equal to 1, SEL equal to 1 and the others equal to 0, right? Yeah, we see. And in S2, we want to transfer the content of rack 1 into rack 2. So what to do? So to transfer the content of this into this, so what we need to do is to set OP to 0. OP must be 0 so that we can pass from this, X is here, go to this, and En should be equal to 1, all right? So this should be 0, En should be equal to 1, and to load into LD2, so this one it should be equal to 1 also, all right? The others is don't care, this one is don't care. Okay, so here we can see that OP must be equal to 0, OP bar, OP must be equal to 0, En must be equal to 1, LD2 must be equal to 1, all right? So the rest is 0. And next is to transfer Y into rack 1. So Y into rack 1. So this is Y now in here, all right? Put into rack 1. So again, SEL must be equal to 1 and LD1 must be equal to 1. All right, so this is 1, this is 1, and the rest 0. And the last one is to add rack 1 add rack 1 add rack 2, which is X plus Y, and we store the result in rack 1. So what to do? Again, we need to go here. We need to go here and this to add. All right, so OP must be set to 1, En must be set to 1, all right, to make the data available here. And we want to save in rack 1, so SEL must be equal to 0 because we want to get the data from this now, 0, and rack 1 LD1 must be equal to 1, all right. Again, to add the content of this to this and save into this means that OP must be equal to 1 to do A plus B, all right, and En must be equal to 1 to make the result available here. And if the result is here, we want to load into rack 1, so LD1 must be equal to 1, right? So see, LD1 equal to 1, SEL equal to 0, this is a must to select the data from the data out into rack 1. OP should be equal to 1, enable should be equal to 1, all right? So this is the sequence. So if we have this sequence, then should be no problem for us to create the control circuit, control unit, all right? It's actually straightforward. So let's do that here, where we can have we will have the state register, and we will have the output logic, and we will have the next state logic, and here is the next state logic, all right, and this is state register, and this is output logic. Okay, so for the output, what you need to have, so the output should be all the control, yeah, we call it control vector, CV, so you can have LD1, LD2, SEL, OP and EN, and this, of course, you will need to have this. And what is the size of your register, or how many flip-flop you need to have? So look at the state. So how many states you have? You have 1, 2, 3, 4, 5. You have 5 states. So to represent up to 5 states, you need to have 3 flip-flops, yeah, minimum 3 flip-flop. Because if you have 2 flip-flop, you can only represent up to 4 states, right? 3 flip-flop you can represent up to 8 states, right? So this must be 3 bit. This must be 3 bit, and again we use more FSM, so you need to have feedback from this to this, and we will use the negative edge triggered clock. All right, and of course you need to have the reset. This is clock. And do we have any input to the controller or finite state machine? Yes, we have here. See, the start here is the input, right? So if the start equal to 1, only then we go to S1. If no, we will remain at state 0. All right. So we have start as our input here. Okay. So this will be our circuit. All right. So we can create the our circuit in Quartus now. So we will need this again, a little bit smaller so that we can see here. All right, we create a new one, new file. The name is CU 52. Okay, this is the name, and can finish there. Module, the name. Of course, we have this clock reset, and all the input here. All right, LD1, LD2, LD3. We don't have LD3. SEL, OP, and we have EN. We have start, and this one we will name as state. This one we will name as next state. All right, and we have one output to this. The name is state. All right, for the simulation purpose, where we can see the state transition of the state later on. So all right, so we have a state output so that we can see later on that how our design transit, the state transition between S0, S1, S2, and so on. All right, so we have input. All are 1 bit, right, including the start. Okay, we have output. This one is not input, right? Sorry, only start and clock. This should be output. Yeah, LD1, LD2, SEL, OP, and EN, all are output. And we have output, and this one should be declared as right also, because we want later on we will describe using behavioral modeling. And this is state output, and it is 3-bit. And we have this signal, which is 3-bit, the next state, and must be declared as right. Right, and we have the FSM, so the state, we will represent the state with the name S1, S0, and so on, right? So we use parameter, must be 2-bit, 3-bit. So S0 equal to 0, S1 equal to 1, S2 equal to 2, S3 equal to 3, S4, we have up to S4 should be equal to 4. That's it. Okay, and we define our state register. Which this one. So we use always clock, and this is negative H triggered clock, and positive H reset. So if reset, the output of this flip-flop with this state should be equal to 0, and our 0 in this case is actually S0. All right, so when reset, we are at S0, and else, if not, so the output must be equal to the next state. Yeah, this one. All right, so this will be this one, and now we want to do this. Always describe these two. All right, so let's name this as next state, and output logic. Right, so now we have what is the sensitivity list. So the input to this, we have state and start, and for this we have state. Yeah, so we have two, start and state. Right, so this, the output for this one, which is this, is dependent on this and this, and for this one the output is dependent on this signal. So we have this. Yeah, so we want to look at the state. Yeah, when we are at state 0, what happened, and when we are at state S1, what happened. So we can use case state. All right, when state is in S0, what to do. So S0, so we will have many statements later on, so we should have the begin. right? So if S0, so what we do here, S0 we just wait, right? And of course we need to have the output actually, or we can use don't care or make it 0, doesn't matter. So if in this S0, so LD1 should be equal to 0, LD2 should be equal to 0, SEL should be equal to 0, OP should be equal to 0, EN should be equal to 0. All right. And we need to have this, right? We have condition, we have input start, so we can use if. All right, start, if start, the next state. Okay, if start equal to 0, next state should be equal to start equal to 1, the next state should be equal to S1, right? Else we should remain at this state, right? Exactly based on this. Yeah, so again, when next state when start equal to 1, so the next state will be S1, and if start equal to 0, we remain at here, just like this. Okay, so that's what we will do, and we should have n here for S0. Should be easy for S0. So for S1, yeah, again we have begin, and L1, LD1, LD2 should be based on this exactly, right? So we can use this. Okay, so LD1 should be equal to 1, SEL should be equal to 1, OP 0, EN 0, and next step should be equal to, we have no condition now. After this operation, we should go to the S2, all right? And we can end here. Okay, done. This is for S1. What about S2? We can use the same one. Just this one is S2. S2, this one is should be 0. So we change this to 0. 0, LD2 equal to 0, SEL equal LD2 equal to 1, SEL equal to 0, yeah, this one. OP equal to 0, EN equal to 1. Okay, SO EN equal to 1. Right? And we have S3, where LD1 equal to 1, SEL equal to 1, OP equal to 0, 0, just like S1, right? So this is okay already. What about S4? S4, LD1 equal to 1, LD2 equal to 0, and SEL should be equal to 0, OP equal to 1, and EN equal to 1, and now should be done. We need to have default. all right, because this state is 3-bit, so we have only how many possibilities here? 1, 2, 3, 4, 5. So we have another 3, so that 3 we can actually use this. Yeah. Or we can say that we put it to 0 and we stay at 0, right? Other than that, in case should be done. And module. Okay, so this should be our CU, and let's save this and try to synthesize. Okay, we have 4 warning, and the warning is output pin are stuck at VCC or ground, so we need to check this. All right, so expand this. OP is stuck at ground. Pin as state 2 is stuck at ground. State 2 is stuck at ground. All right, let's go back and see. Oh yes. All right. First, we look at the OP. Actually, not stuck at ground. We have one here, but this we have this because this one actually state number 2. We look at this next state S2, S2, S2. This is wrong. Actually, this should be S3, and this should be no. This S2. This should be S3. This should be S4, and this is should be S0. Go back to S0, right? And when we have this, so this should be solved, right? Because before this we never go to S4. That's why it says that OP is stuck at ground, yeah, because we only have here. So now the problem should be solved, right? So there is no that warning anymore. So we have one warning only, which is of course the license. Should be no problem there. Okay, so this will be the CU circuit for us, yeah. So now we will create the simulation for this, and before that we need to connect this CU to this DU, all right, and write the test bed to look at the simulation result. Okay, so now it's 9:51, so maybe we have a short break, 10 minutes break before we come back at 10 and look at the simulation.